gaze up at the night sky. For millennia, humanity has looked to the stars, seeking answers, connection, and a sense of our place in the cosmos. We've mapped constellations, tracked planets, and listened intently for any sign that we are not alone. And in the vast, silent theater of space, sometimes we hear a whisper, or more accurately, a sudden, powerful shout. These are fast radio bursts, or FRBs, one of the most perplexing and exciting mysteries in modern astronomy. Imagine you're tuning in old radio, scanning through static. Suddenly, for just a fraction of a second, a perfectly clear signal cuts through the noise before vanishing. That's essentially what our radio telescopes experience with FRBs. These are incredibly intense bursts of radio waves, lasting only a few milliseconds shorter than the blink of an eye. Yet in that fleeting moment, they can release more energy than our sun does in an entire day. They flare up, brilliant and powerful, and then they are gone, leaving astronomers with a tantalizing cosmic puzzle. The story of FRBs began in 2007. Astronomer Duncan Lorimer and his student David Narkovic were combing through archived data from the Parkes Observatory in Australia. They stumbled upon a signal from 2001 that was so strange, so powerful, and so brief. They initially suspected it was a glitch in the equipment. It was a single, isolated burst that seemed to come from far beyond our own Milky Way galaxy. This first discovery, now famously known as the Lorimer burst, was the spark that ignited a new field of astrophysical investigation. For years, this single event was a lonely anomaly. Scientists were skeptical. Was it a terrestrial signal masquerading as something from deep space? A satellite malfunction? A microwave oven opened prematurely in the observatory's kitchen? Believe it or not, that last one was a real theory for a while. But then, more bursts were found. Using telescopes around the world, astronomers began to detect these ephemeral signals, confirming that they were indeed real and of cosmic origin. What makes FRBs so fascinating is not just their power, but their journey. As these radio waves travel across billions of light years, they pass through the tenuous gas and plasma that fills the space between galaxies. This intergalactic medium slows down the radio waves slightly, with lower frequencies being delayed more than higher frequencies. This effect, called dispersion, is a key piece of evidence. By measuring this delay, astronomers can calculate how much material the burst has passed through, which in turn gives them an estimate of its incredible distance from us. Most FRBs originate in galaxies hundreds of millions or even billions of light-years away. They are echoes from the distant universe, carrying secrets of the cosmic web across unimaginable voids. Initially, all the FRBs detected were one-off events. They flashed once and were never heard from again. This made studying them incredibly difficult. You couldn't point a telescope at a spot in the sky and wait, because you had no idea when, or even if, another burst would occur from that location. It was like trying to photograph a single, unpredictable lightning strike. But everything changed in 2012 with the discovery of FRB 121102. This one was different. It repeated, from a single point in the sky, in a dim dwarf galaxy 3 billion light-years away. Bursts were happening again and again. This was a monumental breakthrough. For the first time, astronomers had a persistent target. They could point their most powerful telescopes at this source and study it in detail across the entire electromagnetic spectrum. From radio waves to X-rays, the repeating nature of FRB 121102 ruled out any source that destroys itself, like the collision of two neutron stars. Whatever was causing these bursts had to be a long-lived object or phenomenon. This discovery opened the floodgates, with new, more sensitive radio telescopes coming online. Like the CHIME telescope in Canada, we've gone from detecting a handful of FRBs to cataloging thousands. CHIME, with its huge field of view, scans the sky constantly, catching these fleeting signals almost daily. We've learned that repeaters are common, though many bursts are still single events. Some repeaters have a predictable pattern, flashing during a specific window of activity and then falling silent for a period, almost like a cosmic lighthouse with a regular rotation. Others are completely sporadic, bursting multiple times in an hour and then going quiet for months. This variety in behavior suggests there might not be just one single explanation for all FRBs. We might be looking at several different types of cosmic engines, all capable of producing these spectacular flashes. So, what could they be? The theories are as spectacular as the bursts themselves. One of the leading contenders is a type of neutron star called a magnetar. Magnetars are the most magnetic objects known in the universe. They are the superdense remnants of massive stars that have gone supernova. And they possess magnetic fields hundreds of trillions of times stronger than Earth's. These immense magnetic fields are unstable. They can twist and snap in what are known as starquakes, releasing colossal amounts of energy. In 2020, astronomers detected a fast radio burst coming from a known magnetar within our own Milky Way galaxy. It was a groundbreaking moment, providing the first direct link between an FRB and a specific type of object. While this burst was less powerful than its extragalactic cousins, it strongly suggested that magnetars are, at the very least, one source of these cosmic signals. But the magnetar theory might not be the whole story. What about the extremely energetic non-repeating bursts, Some theories propose cataclysmic events, like the merger of two neutron stars or a neutron star collapsing into a black hole. Such events would be powerful enough to generate a single, titanic burst, but the source would be destroyed in the process, explaining why we never hear from them again. Another fascinating idea involves something called a blitzer in this scenario. A rapidly spinning neutron star, too massive to support itself, is temporarily held up by its own centrifugal force. Eventually, as it spins down, it catastrophically collapses into a black hole, releasing a final, powerful radio burst as its magnetic field is severed. And of course, lurking in the background of every discussion about strange signals from space is the question: could it be aliens? The idea of extraterrestrial intelligence, or ETI, is captivating. Could FRBs be beacons from a distant civilization, perhaps a power source for their starfaring ships, or a massive communication network? While it's an exciting thought, most scientists apply Occam's razor. The simplest explanation is usually the best. We have plausible natural explanations like magnetars that fit the data well. Until we've exhausted all possible natural causes, the ETI hypothesis remains firmly in the realm of speculation. But it's a good reminder that the universe is full of possibilities, and we should keep an open mind. Regardless of their origin, FRBs are more than just a mystery. They are a revolutionary new tool for exploring the universe. Think of them as cosmic flashbulbs. By studying how their light, or in this case, their radio waves, is stretched and scattered on its journey to us, we can map the distribution of matter between galaxies. This is matter that is incredibly difficult to detect otherwise. It's the so-called missing matter that theories predict but that we've struggled to find. FRBs are lighting up this hidden cosmic web, allowing us to weigh the universe and understand its large-scale structure in unprecedented detail. The future of FRB research is incredibly bright. New and upcoming telescopes, like the Square Kilometer Array, will have the sensitivity and resolution to pinpoint thousands more of these bursts with incredible precision. We'll be able to zoom in on their host galaxies, study their local environments, and see if they live in star-forming regions, near a galactic center, or out in the galactic suburbs. Each new detection, each piece of the puzzle, brings us closer to understanding the physics behind these extraordinary events. We live in a remarkable era of discovery. We are the first generation of humans to know of these powerful, millisecond-long whispers from across the universe. They are a humbling reminder of the sheer scale and power of the cosmos, and of how much we still have to learn. Each burst is a postcard from a distant galaxy, a message written in the language of physics, traveling for billions of years to land in our telescopes. The challenge, and the joy, is learning how to read it. The silence of space is not empty. It's filled with secrets, waiting for a patient ear, and as we continue to listen, who knows what other wonders we might hear. Thanks for watching.